Hello and welcome, dear students. Today we are going to discuss an important topic, that is industrial production of alcohols. The main objectives of today's lecture are to get the basic idea about alcohols, to understand different processes of ethanol preparation, to get an idea about different processes of methanol production, to briefly understand the process of isopropanol production, and finally to give students a brief idea about the use of alcohols as biofuels. Basic idea about alcohols. Alcohols are the organic compounds characterized by one or more hydroxyl groups attached to a carbon atom of an alkyl group, that's hydrocarbon chain. Alcohols may be considered as organic derivatives of water in which one of the hydrogen atoms has been replaced by an alkyl group, typically represented by R in organic structures. For example, in ethanol or ethyl alcohol, the alkyl group is the ethyl group, that is CH2CH3. Alcohols are among the most common organic compounds. They are used as sweeteners and in making perfumes, or valuable intermediates in the synthesis of other compounds, and are among the most abundantly produced organic chemicals in industry. Perhaps the two best known alcohols are ethanol and methanol. Ethanol is used in toiletries, pharmaceuticals, and fuels, and it is used to sterilize hospital instruments. It's moreover the alcohol in alcoholic beverages. The anesthetic ether is also made from ethanol. Methanol is used as a solvent, as a raw material for manufacture of formaldehyde and special resins, in special fuels, in antifreeze, and for cleaning metals. Alcohols may be classified as primary, secondary, or tertiary, according to which carbon of the alkyl group is bonded to the hydroxyl group. Most alcohols are colorless liquids or solids at room temperature. Alcohols of low molecular weight are highly soluble in water. With increasing molecular weight, they become less soluble in water, and their boiling points, vapor pressures, densities, and viscosities increase. Structure. Similar to water, an alcohol can be pictured as having an sp3 hybridized tetrahedral oxygen atom with non-bonding pairs of electrons occupying two of the four sp3 hybrid orbitals. Alkyl groups are generally bulkier than hydrogen atoms. However, so the ROH bond angle in alcohols is generally larger than the 104.5 degree hydrogen-oxygen bond angle in water. For example, the 108.9 degree bond angle in methanol shows the effect of methyl group, which is larger than the hydrogen atom of water. Classification of alcohols. Alcohols fall into different classes depending on how the OH group is positioned on the chain of carbon atoms. There are some chemical differences between the various types. Primary alcohols. In a primary alcohol, the carbon which carries the OH group is only attached to one alkyl group. Example, ethanol, propane 1-ol, 2-methyl propane 1-ol. There is an exception to this. Methanol CH3OH is counted as a primary alcohol even though there are no alkyl groups attached to the carbon with the OH group on it. Secondary alcohols. In a secondary alcohol, the carbon with the OH group attached is joined directly to two alkyl groups, which may be the same or different. Examples: propane 2-ol, butane 2-ol, pentane 3-ol. Tertiary alcohols. In a tertiary alcohol, the carbon atom holding the OH group is attached directly to three alkyl groups, which may be any combination of same or different. Examples: 2-methyl propanetol, 2-methyl butanetol. Different processes of ethanol preparation. Ethyl alcohol production from carbohydrates by fermentation. Ethanol can be produced by fermentation of any carbohydrate containing a fermentable sugar or a polysaccharide that can be hydrolyzed to a fermentable sugar. The equation that describes the net result of alcoholic fermentation by yeast is C6H12O6, which gives 2 molecules of C2H5OH plus 2 molecules of carbon dioxide. It indicates that sugar is the substrate and the process is anaerobic. Selected strains of Saccharomyces cerevisiae are commonly employed for fermentation. It's imperative that the strain must have a high tolerance for alcohol, must grow vigorously and produce a large quantity of alcohol. Ethanol production from molasses by fermentation. Sugar industries produce molasses from the sugarcane processing. Molasses have 50 to 55% concentration of sugar in the form of sucrose with chemical formula C12H22O11. This source of compound is used for preparing ethanol. Ethanol in the form of absolute and rectified spirit can be made from molasses. Basic raw materials for an industry to produce 1 ton of ethanol requires molasses up to 5.6 tons, sulfuric acid 27 kg and ammonium sulfate 2.5 kg. The chemical reactions involved for ethanol production from molasses: main reaction C12H22O11 plus H2O, which gives 2 molecules of C6H12O6 with enzyme invertase. C6H12O6 gives 2 molecules of C2H5OH plus twice carbon dioxide with enzyme zymase. Ethanol production from starch and sugar-based materials. Current commercial production of ethanol is based almost exclusively on starch and sugar-based feedstocks. In the United States, the ethanol industry is dominated by corn, with 91.5% of production capacity from facilities using corn alone and another 7.9% of capacity from facilities using a blend of corn and other grain, example corn and millet, with corn as the primary feedstock. Facilities using other grains, example wheat, millet, without corn make up an additional 0.4% of capacity. There are two main processes of producing ethanol from corn: dry milling and wet milling. Both processes involve breaking down the starch in the corn kernel into simple sugars and then fermenting the sugars to create ethanol. The primary difference between the two methods is whether the entire kernel is processed as in corn dry milling or if the corn kernel is first broken down into its individual components, that's germ, fiber, gluten and starch, prior to processing as in corn wet milling. Dry mill ethanol plants generally produce only one primary co-product, distillers grain with solubles, which can be sold wet or dried for use as animal feed. In contrast, the corn wet milling process of separating shelled corn into its components prior to processing. It increases the number of co-products realized, usually gluten feed, gluten meal, food grade corn oil and distillers grain with solubles. Now we will discuss alcoholic beverages. These products of alcoholic fermentations originated in spontaneous fermentation processes are of great antiquity. However, it is only in recent years that modern methods of industrial microbiology have been applied to their manufacture. In principle, the production of alcoholic beverages is similar to the production of industrial ethyl alcohol. These fermentation processes do not suffer competition from synthetic products. This is because the character of beverage is dependent upon interactions between a variety of biological factors that have not yet been denied in chemical or physical terms. In beverage production, refinements are introduced with respect to flavor, aroma, color, and sanitation that are not necessary in the making of industrial alcohol. Beer. Beer is made by the yeast fermentation of grains to ethanol and carbon dioxide. There are 5 major steps in the manufacture of beer from grain. These are malting, mashing, fermenting, maturing, and finishing. Malting and mashing are concerned with the conversion of starch into fermentable form such as maltose or glucose. The chief raw material is malt, which is germinated barley that has been dried and ground. It contains starch, proteins, and high concentration of amylases and proteinases. Amylases convert the starch into fermentable sugar. Mold amylase, derived from Aspergillus oryzae, is sometimes used for same purpose. Ground malt is mashed in warm water to bring about the digestion of starch and proteins. The aqueous extract contains dextrins, maltose, and other sugars, protein breakdown products, minerals, and various growth factors. This is a rich nutrient medium and is called beer wort. The beer wort is filtered and hops are added. Hops are the flowers of Humulus lupulus. They are added for flavor, color, aroma, and for mild antibacterial activity to prevent the growth of spoilage bacteria. Wine. Wine is the product made by the normal alcoholic fermentation of the juice of sound, ripe grapes and the usual cellar treatment. Beverages produced by the alcoholic fermentation of other fruits and certain vegetable products are also called wines. For example, peach wine, orange wine, cherry wine. Wine making is a much simpler process. It can be made by a direct fermentation of sugars, that is, glucose and fructose, instead of starch, which requires hydrolysis to yield sugars. Many fruits have the wine yeast Saccharomyces cerevisiae varieties ellipsoides on them. All that is necessary is to crush the fruits. An alcoholic fermentation starts spontaneously. The characteristic qualities of famous wines are attributed in part to strains of yeast found in certain localities. However, undesirable molds, wild yeasts, and bacteria are also likely to be present, and the fermentation may not give a predictably good product. Many winemakers now destroy natural yeasts by adding sulfur dioxide to the raw juice. The grapes are crushed carefully and the juice is collected. To the raw juice or must, sulfur dioxide is added as sodium metabisulfite. The must is then inoculated with a starter culture of a selected strain of Saccharomyces cerevisiae variety ellipsoideus. At the start, the must is aerated slightly to promote vigorous yeast growth. Once the fermentation sets in, the rapid production of carbon dioxide maintains anaerobic condition. The temperature of fermentation is usually 25 to 30 degrees Celsius, and the process may extend from few days to 2 weeks. The yield of ethanol varies from 7 to 15% by volume. The wine is placed in large casks to settle, clarify and age for 2 to 5 years to develop a good flavor and aroma. Wines are endless in their varieties and differ in so many attributes that it is difficult to classify them. According to color, the two most basic types are red and white wine. In making red wines, the grapes are crushed and stemmed, but the skins and seeds are left in the must. White wines are made from white grapes or from the juice of grapes from which the skins have been removed. Dry wines are those which contain too little sugar to be detected by taste. In sweet wines, the sugar content is high enough to be detected by taste. Sparkling wines contain carbon dioxide. They are made effervescent by secondary fermentation in closed containers, generally in the bottle itself. Still wines are those which do not contain carbon dioxide. Fortified wines contain added alcohol in the form of brandy. High quality red wine grapes have colorless juice. The entire red color is in the grape skins, and winemakers must leave the juice in contact with the skins for a considerable time to extract the color. Red wine is made by crushing the grapes and then fermenting the juice, the pulp, the skins, and the seeds together for several days. Near the end of a sugar fermentation, a wine press is used to separate the liquid from the solid materials. White wine is made by a different process. First, the grapes are crushed and pressed immediately to separate the juice from the solids. After pressing, the skins, stems, and seeds are discarded, and the juice is cooled to a low temperature. Then the cold juice is allowed to settle for several hours, and the clear juice is decanted off the residue before it is fermented. White wine is made by fermenting clarified juice. These are the fundamental differences between making quality, red wine and white wine. At first glance, the two wine-making processes may appear similar because several steps are identical. Nevertheless, the steps are done in a different sequence, and the sequence makes a large change in wine characteristics. Different processes of methanol production. Methanol production from biomass. In contrast to ethanol, methanol can rather easily be produced from virtually all biomass such as wood, algae, agriculture waste, and municipal waste through gasification. Production from biomass does, however, offer challenges that need to be addressed, especially regarding the cost of production. The conventional method to produce methanol from biomass is through gasification of the feedstock material. The gasification process of biomass is similar to the synthesis gas process from coal. For gasification of biomass, the feedstock is first dried and pulverized. The moist content should generally be no higher than 15 to 20 weight percentage. The first step in a two-step gasification process is called pyrolysis or destructive distillation. The dried biomass is heated to 400 to 600 degrees Celsius in an oxygen-deficient environment to prevent complete combustion. Carbon monoxide, carbon dioxide, hydrogen, methane, as well as water and volatile tars are released. The remaining biomass, called charcoal, is further reacted with oxygen at high temperature to produce mainly carbon monoxide. Methanol production in chemical industry. Methanol is primarily used in making other chemicals. About 40% of methanol is converted to formaldehyde and from there into products such as plastics, plywood, paints, explosives, permanent pressed textiles. Methanol is manufactured from synthesis gas, which is a mixture of carbon monoxide and hydrogen. The feedstock over the last 40 or more years has been oil or natural gas. However, two developments have occurred over recent years. In one, particularly in China, coal rather than natural gas or oil is being used. In the second, there have been major developments to produce methanol, which is largely green, environment-friendly technique. Any solid biomass, for example, agricultural, city and industrial waste can be used to make synthesis gas using techniques similar to its production from coal. More recent developments include a manufacturing plant in the Netherlands which is using liquid propane 1,2,3-triol, that is glycerol, a byproduct from the production of biodiesel from animal fats and vegetable oils to produce the gas. Different processes of isopropanol production. Isopropanol, that is propan-2-ol, also called dimethyl carbinol, is a compound with the chemical formula C3H8O. It is a colorless, flammable chemical compound with a strong odor. As a propyl group linked to a hydroxyl group, it is the simplest example of a secondary alcohol. It has a wide variety of industrial and household uses. Production. This compound is primarily produced by combining water and propene in a hydration reaction. It is also produced by hydrogenating acetone. Indirect hydration. The indirect process reacts propene with sulfuric acid to form a mixture of sulfate esters. Subsequent hydrolysis of these esters by steam produces isopropyl alcohol, which is distilled. Diisopropyl ether is a significant byproduct of this process. It is recycled back to the process and hydrolyzed to give the desired product. Direct hydration. Direct hydration reacts propene and water either in gas phase or in liquid phase at high pressures in the presence of solid or supported acidic catalysts. High purity propylene tends to be required for this type of process. Hydrogenation of acetone. Crude acetone is hydrogenated in the liquid phase over Raney nickel or a mixture of copper and chromium oxide to give isopropyl alcohol. This process is useful when coupled with excess acetone production, such as the Sumine process. Uses of alcohol as biofuels. Bioethanol, an alcohol fuel, is the most common biofuel worldwide, made by fermentation mostly from carbohydrates, produced in sugar or starch crops such as corn, wheat, sugar beets, sugarcane, or sweet sorghum. Molasses and any sugar or starch from which alcoholic beverages such as whiskey can be made, such as potato and fruit waste, etc. Cellulosic biomass derived from non-food sources such as trees and grasses is also being developed as a feedstock for ethanol production. The ethanol production methods used are enzyme digestion to release sugars from stored starches, fermentation of sugars, distillation, and drying. The distillation process requires significant energy input for heat, sometimes unsustainable natural gas fossil fuel. But cellulosic biomass such as bagasse, the waste left after sugarcane is pressed to extract its juice, is the most common fuel in Brazil. Wood pellets, wood chips, and also waste heat are more common in Europe. Ethanol can be used as a fuel for vehicles in its pure form, but it is usually used as a gasoline additive to increase octane and improve vehicle emissions because ethanol has about half the energy per mass of gasoline, which means it takes twice as much ethanol to get the same energy. Biobutanol, also called biogasoline, is often claimed to provide a direct replacement for gasoline because it can be used directly in a gasoline engines. Biobutanol has slightly less energy than gasoline but can run in any car that uses gasoline without the need for modification to engine components. Butanol, C4H9OH, is formed by acetone butanol ethanol fermentation, and experimental modifications of the process show potentially high net energy gains with butanol as the only liquid product. Butanol will produce more energy and allegedly can be burned straight in existing gasoline engines without modification to the engine or car, and is less corrosive and less water soluble than ethanol. Biomethanol is produced from biomass. Methanol has about one-third to one-half as much energy as methane. Methanol is a liquid and easy to transport, where methane is a gas that must be compressed for transportation. The methanol economy is an alternative to the hydrogen economy compared to today's hydrogen production from natural gas. With this, we come to the end of today's topic. Hope you have enjoyed and understood the lecture. Thanks for watching. Goodbye.